Saturn is a beautiful planet with colorful rings, but it cannot be considered a failed star. Failed stars, known as brown dwarfs, are smaller and don't have enough mass to sustain nuclear fusion reactions. Saturn didn't have enough mass to become a star, and even if it tried, there wouldn't be enough material for it to happen. Jupiter, although larger than Saturn, also doesn't have enough mass to be a star. Brown dwarfs are different from regular stars in terms of mass, formation, and energy production. Jupiter needs to increase its mass by over 1,000 times to become as large as our Sun. However, the smallest stars, known as red dwarfs, can be only 7.5% of the mass of the Sun. If Jupiter wanted to become a star, it would be more realistic for it to become a red dwarf, requiring an increase in mass by a factor of about 80. There is even a red dwarf in the Milky Way galaxy that is smaller than Jupiter, capable of supporting hydrogen fusion. If Jupiter and Saturn were to collide, they would not merge into one planet or a star. In a head-on collision, the planets would destroy each other, with their gas envelopes eliminated and solid cores sent into space. In a collision at an angle, the planets might survive but would lose a significant portion of their material. If the gas giants slid across each other at an oblique angle, their shapes would change, but not their composition or mass. Regarding Earth and another solar system, there have been over 4,100 planets discovered outside our solar system. Most of them are icy or gas giants, but there are approximately 161 planets similar to Earth. In the Alpha Centauri constellation, which is close to us, there are 3 stars, 2 of which are called Alpha Centauri A and Alpha Centauri B. These stars are bright and can look like one in the southern hemisphere. Proxima Centauri is a smaller and colder star located 4.5 light-years away from us. Its companion planet, Proxima b, is slightly larger and more massive than Earth and located in the habitable zone. The planet may have water and potentially support life, although more research is needed. If Earth were in the Alpha Centauri system, closer to Proxima Centauri, several adjustments would be necessary. The new planet, New Earth, would need to be around 25 times closer to its star to avoid extreme cold. However, Proxima Centauri is a flare star, emitting strong radiation and stellar winds. To protect against this, New Earth would require a thick atmosphere and magnetic fields. The rotation of Proxima Centauri's planets is uncertain, and if they were tidally locked like Earth's moon, one side of New Earth would be scorching while the other would be frozen. However, settling in a middle region would provide a more comfortable temperature of around 70 degrees Fahrenheit. The new planet would have more water and a varied climate with strong winds and heavy rains. The flora would be lush, with low trees, and there would be large flying animals like dragonflies with a wingspan of 16 feet. Despite some challenges, settling on New Earth in the Alpha Centauri system would offer a diverse and potentially habitable environment with its own unique characteristics. In the Alpha Centauri system, there are 4 suns. Proxima Centauri is our main sun, and we can also see 2 bright stars called Alpha Centauri. Additionally, our old sun appears as a distant bright star. There are planets nearby, including Proxima Centauri C, which offers beautiful night views due to its surrounding cosmic dust belts. This creates a beautiful green planet. Moving to Proxima Centauri would be appealing to me. How about you? Unfortunately, rotating near both Alpha Centauri A and B simultaneously is not possible. However, let's imagine being near Alpha Centauri A, where temperatures range from -100 degrees Fahrenheit at the South Pole to 113 degrees Fahrenheit at the equator. The day duration is 24 hours and the orbital period is 1 year and 1 month. The conditions are similar to Earth, and the changes in seasons and temperatures are not significant. It's essential to consider that these conditions assume perfect circumstances. Any slight changes, such as thinner atmosphere or greater distance from the star, could have unfavorable outcomes. Luckily, the universe offers a high chance of finding habitable planets, with an estimated 15 million potential planets for life. In South America's Atacama Desert in Chile, you can witness significant astronomical events, such as a black hole absorbing a massive star. The astronomers who observed this event are the same scientists who confirmed the presence of a supermassive black hole at the center of our Milky Way galaxy and captured its image. In September 2019, an unprecedented event occurred relatively close to Earth, only 215 million light-years away, considered close in astronomical terms. It involved a star, similar in size to our Sun, and a massive black hole that weighed 1 billion times more than the star. The black hole's gravitational force was so strong that nothing, even light, could escape it. As the star entered the black hole's gravitational field, it began to stretch due to the powerful force of attraction, a phenomenon known as spaghettification. The outer layers of the star, forming its crown, started to shrink, and the hot plasma reached the event horizon, the boundary of the black hole. At this point, the star's particles were inevitably pulled into the singularity, the black hole's core. Observers could see a croissant-like event horizon and the chaotic movement of light particles. The particles appeared to move more slowly due to the curvature of space-time caused by the black hole's enormity. After absorbing the star's material, the black hole emitted powerful energy rays accompanied by intense flashes. Scientists could detect this process, akin to observing stardust and particles in the black hole's event horizon. Approximately half of the star's weight was expelled into space as dust and glowing particles, while the other half was entirely absorbed by the black hole. In a simulated experiment, a drone is sent towards a black hole, starting at a safe distance and gradually approaching the event horizon. As it gets closer, the drone begins to stretch like spaghetti and eventually reaches the event horizon, where all light becomes blue due to gravitational blue shift. The drone continues to fall into the black hole, experiencing a slowed passage of time. Eventually, it reaches the singularity at the heart of the black hole before being thrown back out into outer space. Returning from a black hole is theoretical, and some speculate that black holes could serve as wormholes to distant places. However, these theories remain fictional at this point. Detecting black holes can be challenging as they do not emit light and can only be detected through gravity anomalies. Scientists believe there are numerous black holes in the universe, forming when massive stars collapse. Black holes have their own lifetimes and can shrink over time due to Hawking radiation.